Good morning, everybody, or good afternoon, I guess now. My name is Jim Nostad. My company is CFAR Building Analytics. We do life cycle cost analysis of buildings. And I'm going to talk to you today about some things that can help you prevent these uh, horrific case studies. And they're pretty simple and they're going to be pretty short, but also I'll just carry on uh, with those. So, the first thing is, and if we were in a room where we could interact a little bit better, I'd ask you, how much does it cost to operate and maintain a building? And so I'm going to create a little of example here, but suppose you want to construct a building that's $1 million, and it really doesn't matter what size it is and what dollar value, but because all the same principles apply. So if the construction cost is $1 million, the design cost is typically about 10% of that, or $100,000, but the total cost of building ownership is between 7 and $10 million. So there's a huge difference there. And so the first question is, what is the largest cost? Now, this is a trick question. No, it's not. It's obviously the total cost of building ownership is the largest cost. And what is the smallest cost? Well, it's obviously design cost, but what cost just a minute, my screen is being covered a by the video on the side. Um, so what cost should we focus on? Well, everybody's going to say we should focus on the biggest cost, and that's true. But at the same time, what has or who has the largest impact on that total cost of building ownership? And it's really the design team. And but the design team is only 10% of the construction costs and only 1% of the total cost of building ownership. So there's a where we focus on the construction cost most often and the design cost, but what we really need to do is get the design team the money and the time that they need so that they can really affect the total cost of building ownership. And the way I summarize this is hire the best design construction team that you can find and pay them well. I'm not saying pay them extravagantly. It would make all these architects and engineers go crazy, but we would you need to have a reasonable design budget in order to lower your total cost of building ownership. And I have been in many meetings over the years where we're trying to chisel down the design consultant cost, and it's actually um, the wrong way to go. So the next thing I want to talk about is sort of it's really about the design and how it's done. And architects have a saying that says form follows function. Well, what does that mean? Well, the building must function well first, and then it can look good. And so let's talk about what the function of the building is first. Well, it has to meet the needs of the occupants. It has to have good indoor environmental or air quality. Um, it has to have a low total cost of building ownership so that it's economical to own and operate. It has to have a low energy consumption and greenhouse gas emissions. And we have to use durable, long life materials, or otherwise the building won't last and it will cost you more. And we also want to have now low operational and material carbon emissions. And then on the form side, um, this is something that I took from Joe Steebrook, and it really makes all the architects' heads swell up a little bit, but I think it's really important. In order for buildings to last a long time, people have to take care of them. Pretty obvious. Now, in order for people to take care of them, people have to want to take care of them. And guess what? People don't take care of ugly things. Ugliness is not sustainable. And I think this is amazingly true. You go around and look at the buildings that get maintained just in your city and in your neighborhood. And then and people don't want to live and work in a building, um, and or people need to want to live and work in a building, only then will they take care of it. And then that's why beautiful things are important, and that's why architecture is important. So if it doesn't look good and it isn't going to function well first, then you're not going to have a sustainable building. And I want to hit a couple last quick points here. Um, this really relates to how we're currently designing buildings. First of all, we always get a budget not to exceed. The second thing is we design the building enclosure to code. The building enclosure is the walls, the roof, or some people call it the building envelope. Decrease the energy with a fancy mechanical system, and this makes all the mechanical engineers' heads swell up because we like to design really um, fancy mechanical systems. And then when the cost is too high, we apply devalue engineering to take out all the good stuff. Now, it's typically called value engineering, but I call it devalue engineering because what happens is most of the good stuff gets taken out, and most of that relates to how well it's insulated and how energy efficient it is. And the owner gets a building that meets his budget, but he has a building that has high operating and maintenance costs forever. So, what I'm suggesting for a new design process is educate the design team about the total cost of building ownership. What does it cost to own and operate that building? Use an integrated project delivery team to design to a budget. And the integrated project delivery team is where the architects, engineers, and contractors all work together, and the owner work together on the design, and create options to optimize the design based on the lowest total cost of building ownership, not on just the lowest energy, but on the lowest total cost of building ownership. And then design to a net zero goal, um, because that's where we need to be. And if you don't give the design team the goal of designing to a net zero building, you'll never ever get that goal. And then you need to design a high performance building enclosure, again, the building envelope. And then you need a high efficiency, all electric mechanical system, probably geothermal, because it isn't going to use fossil fuels. And then add renewables to achieve net zero. And you do the renewables last in the design because that means you're going to have a smaller number of solar panels or wind turbines or whatever it is, and because the load is small. And then the last thing is enjoy the savings. And I think that's all I have, Laura. Turn it back to you.
All right. So next up, we have Ed Lorenz talking about geothermal. Take it away, Ed.
What else is there but geothermal? Um, okay, I always found it a lot easier to learn from other people's mistakes. A lot cheaper to do that than my own. Not saying I haven't made my share of my own mistakes. I certainly have. But if you can learn from other people's mistakes, that's going to be a lot better for you. One thing I found is that energy modeling is absolutely critical to designing a ground source system that's going to operate efficiently for the life of the building, and it's going to have a lower capital cost. This is an example of a building, about a 46,000 square foot building that we did some forensic analysis on in Fergus Falls, Minnesota. They had 150 tons of heat pump equipment in there, 10 compressors in 5 heat pumps. And it was kind of revealing that when I talked to the building operator, they said the most compressors he's ever seen running since the system was installed in 1998 was 5 out of the 10 compressors, kind of suggesting that the system was grossly oversized by at least double. And that meant that the circulation pumps in the ground loop were much bigger than they needed to be. And to be fair, the in 1998, when the system was installed, variable frequency drive or variable speed circulation pumps and controls were a lot more expensive than they are now. But but to realize that the pumps are they're a parasitic load on a system, but they're absolutely necessary. Otherwise, you can't move the heat from the ground to the building, or vice versa. So what that meant was that the system was a way oversized. They designed it for a flow rate of about 450 gallons per minute, because that's how much equipment was installed, even though that's only half of it had ever run at any one time. So it means that the system was operating at full speed all of the time. And when you think about the friction losses through the pipes and the equipment, that generates heat that is eventually transferred to the ground, which by itself can overheat the ground. So basically, what they should have had in there is 3 heat pumps instead of 5. So they spent a lot more money installing the additional heat pumps. They installed a bigger pump than was needed. That also meant that it cost them in electricity alone about roughly $7,400 per year. And all that generated heat that ended up in the ground heat exchanger, which over time, because the earth is a very good poor conductor of heat, the heat that you put into it basically sits around there for quite a while. And what they ended up doing was connecting the ground heat exchanger to a well water system that they already had. So they were running about 40 gallons per minute, starting in probably about June every year, just to make sure that the temperature wasn't going to increase over time. That also meant the extra heat didn't allow the temperature of the ground heat exchanger to cool off during the winter. So because they dumped so much heat in there, and they kept that under control. So it was operating a bit more efficiently in heating, but the ambient ground temperature in that area is about 45 degrees, 47 degrees, same as it is in Winnipeg. It never dropped below that, even though they were heating with it every year. So what that meant is, and they were keeping track of how much energy was transferred to the groundwater every year, roughly 300 to 400,000 kilowatt hours worth of heat every year. That's about the same amount of energy that was being transferred to the ground from the circulation pump just through friction losses. So what that meant was that they were running a well pump unnecessarily. They were spending about $7,400 per year just on electricity to run the pump. And if they made a few changes to the system, this is what the temperature of the ground heat exchanger had been for these 3 years. Here's what it probably could have been. It would have dropped lower in temperature in the winter, but well within the operating parameters of the equipment. Would have bumped it up to about the same temperature during the winter because you haven't got the extra energy from circulating all the fluid through the ground loop if that was sized properly. So the changes here's the way the system was built originally. They've got a 15 horsepower pump and a water to ground heat exchanger, 5 heat pumps. And by making a few changes to it, getting rid of or not using the 2 extra heat pumps, that meant lower operating costs, lower capital costs, lower maintenance costs. Replacing the 15 horsepower pump with a 5 horsepower pump, again, lower capital cost, lower operating cost, lower maintenance. Eliminate the groundwater to ground heat exchanger, again, reducing capital and operating costs. Then they could install motorized valves that shut the flow off to the heat pumps so that they could properly control a variable speed drive on these pumps, would reduce energy consumption pretty substantially by probably about 90%. And then free up some mechanical room space if it had been designed properly in the first place. And that would have potentially reduced the electrical service to the building. So there's implications all the way throughout the whole system, through every aspect of it. So basically, really understanding that the hourly energy loads really can help inform the design of the building, mechanical system, and if you want to design a cost-effective and efficient and long-lasting ground source heat pump system, it'll result in lower capital cost, lower operating efficiency, or better operating efficiency, and lower maintenance costs. So that's basically the lessons that I've learned. This is only one of about half a dozen buildings that I've seen where pumping energy alone, which is a parasitic load on a system, is a pretty critical part of the proper design. Yeah, thank you.
Our next story is coming to us from Donald. Take it away.
We did a retrofit to my own home, 2011, built in 1956. retrofitting your own home is rewarding, exhausting, unending, terrifying, expensive, and affordable. Um, I believe it's all those things. But we'll get into that. So one of the things that the learning experiences is to make detailed plans and drawings. The plans should be, talk out what you want to do, what you want to achieve. The drawings should reflect that if you're having somebody do the work or you're doing the work yourselves. In this particular case, trying to get back to my notes. I started off with a concept. We'd done some retrofitting, so we thought, okay, we're gonna do this to our own house. I had a season from May to October to do it. I was working full time. My wife was working full time. We thought it was achievable. So full basement insulation upgrade on the exterior, full Larson Truss addition with cellulose. New windows, dual doors in all the openings. Um, I did most of the excavation by hand because of limited space. Um, so it was challenging. Um, my design evolved according to reality, I would say. Things changed over time. We weren't able to do the roof until 10 years after we did the other portion of the project. Um, Scary things that we encountered along the way. There's a fireplace in the basement of the house. Um, it was removing a lot of air from the building. It was probably the chief source of ventilation in the building when we moved in. Ancient HVAC equipment and services. You can see most of it there. You can see the 60 amp fused panel, a couple of breaker box. You can see the old gas furnace. You can see the old gas hot water tank. That was the original furnace. Heat exchanger was cracked. It needed replacement. What do you do? The reinforced concrete steps that we didn't know were that heavily reinforced. We didn't know that they carried all the way down to the base of the footing. And so all that had to be removed. I decided to try and punch the holes for the new HRV, the ventilation system myself. You can see I encountered some rebar. Very difficult when you're just operating on your own with a hammer drill and some chisels. I learned to just hire the pros. The corers could have done that in about an hour, had nice clean holes, wouldn't have taken all of an afternoon. There's a middle picture of the trench that we excavated. It's kind of hard to see, but I've got some of the backfill is because I was doing this by hand. The backfill is being kept out of the hole by some boards you can see, and you can also see kind of a flake of materials come off the side of the trench and fallen into the bottom. That happened overnight, but that would have squished me like a bug. So trench work is dangerous, so plan accordingly. Make sure you have room for all that material. Plan ahead. And then we discovered the terribly patched bathroom window that had been covered up at some point and had been causing problems. We were just trying to figure out how to make it so that it wasn't going to cause more problems. My chief concern with this style of retrofit is the building is a system. You have to account for all of the moving parts, the HVAC, your thermal bridges, how you're handling moisture, as we've learned in a few cases here already. One of my chief regrets is placing our windows to the outside of the wall system, to the upgraded wall, as you can see. From the inside, it creates a very deep window well, which is attractive for all sorts of things. People like sitting on them. They like putting knickknacks and candles and plants and things like that. But it creates a dead air space that fosters, even with decent windows, It fosters moisture production at the bottom of the window, especially on a big north-facing window like this. It never see or it sees very little sun, and so if I had placed the window in the wall, it would have helped a little bit. It would have been in the insulation, helped increase the performance of the windows all around, not just this one. Um, One of the other regrets is that on the sides of the building where I had the space, I didn't add more insulation. Um, the walls are R42 as or approximately R40 as they sit. Um, but on the north and south sides, I could have gone deeper to whatever I had chosen to go. The only restrictions were in my head because I could have very easily modified the truss that I was building. It would have added a few more bits of material, but uh, not restricting anything really. So it was all in my head that I didn't want to change up. I just wanted to keep things the same. The image on the right is how we do our retrofits now, 16 inches, but you can also see that there's a solid sheet of plywood in behind there. And on my retrofit, you can see the old gypsum lath that's the inside wall. So I was relying on the airtight drywall approach for airtightness, which I wouldn't really recommend. And now we try to use that taped plywood system that ensures airtightness. That's the key. You have control over your airtightness. So that's my chief learnings from this. There's a couple of other things. Um, Support from friends and family is very important if you're doing something like this on your own. This is also from your partner. Support from your partner is crucial. Uh, those of you who know our family, my other one was to listen to my Uncle Randy. He had some good advice for us. Listen to your parents if they're offering you advice, if you can possibly do so. Uh, More insulation in most cases is probably a good thing. And I'm sorry, but I didn't finish off with images. The increased air tightness is probably as or more important. And my final lesson is that buildings are systems with many components working together. Without forethought and planning and an experienced builder, things can get complicated and go sideways on you in a hurry.
Well, thank you so much, Don, for sharing that. We're now moving on to our next uh, community shared story that Chantel is going to read for us this time. Take it away.
Thanks, Laura. This next story is about expanded polystyrene, also known as EPS, which is a lightweight and rigid foam material that provides a cost effective and energy efficient insulation. When retrofitting my personal home, I used multiple layers of a graphite EPS exterior insulation to boost the R value of my walls. It was a great product, installed easily, fairly cost effective. To my horror, I ended up with a large amount of small cutoffs, which had no use to me. EPS is a cost effective, great insulator. Some types even have a lower embodied carbon than mineral wool. It is also a petroleum based product and one that does not biodegrade for 500 plus years. So it is a product that we need to recycle. My solution to these extra pieces that I couldn't use was to chip it up and put it in my attic for added insulation.
All right. Thank you so much. That was a great solution that this person came up with. But what do we think was the lesson that was learned through this particular horror story of having too many little ends there? So, after using graphite ESP insulation, a homeowner realized the environmental impact of unused cutoffs. EPS is a petroleum-based foam insulation with strong insulating properties, but a long life cycle. I read someplace that it can take 500 years to go away. All right, so this is another community one shared. So again, no pictures for this one, but still lesson.
Okay, so the adoption of energy modeling in multifamily design by one client supported the deletion of additional outboard insulation installed in previous projects using the performance path for compliance. Practically, the effective R value of the wall assemblies was reduced by as much as 20% by deleting the outboard insulation.
All right, everybody. What do we think the lesson is here? So, what is the important lesson for using energy modeling in multifamily building designs? What could it be? Is it conduct energy modeling early in the project to guide some initial decisions? Is it use modeling results to help set design goals, but adjust as needed during construction? Is it focus on energy modeling primarily to meet compliance requirements? Or is it involve the right team and use model results to guide best practices throughout the project? The correct answer was involve the right team and use model results to guide best practices throughout the project. That was the lesson this person learned. Okay, so moving right along, we're going to hear now from Cindy, who has a ongoing horror story that I know she's excited to share and we're thankful for.
My situation is that I've bought a 1948 home, and I think it everybody beforehand has said exactly a lot of the lessons and issues that I've had. I bought a lovely home for all the reasons that Jim was talking about, that are about a building and home. This is a lovely spot. We bought it because of the lot. You can see there are a lot of trees, and it has a little notoriety as an architect designed home by James Donahue. So there was some historical relevance to this, and we were looking to we were looking to live our values and retrofit a home. So we are coming into this with our eyes open. A 1948 home is going to have some issues, and these are some of the issues you've seen. We expected issues that were manifesting in the home as we saw it. So this is a massive ice dam on the south side, so we knew there are insulation problems. And so one of the first things we did as we started this project was to commit to a deep energy retrofit. Um, so we fell in love with the house, and then the house tried to kill us. There were many things that we expected, like low insulation, but then in the process, we also found asbestos, even though the previous owners had declared that asbestos had been removed. We, by accident, discovered radon in the house, and we'll talk to you about that. And also, having had a 75-year plus history, there was living in the walls or existing in the walls, evidence of irregularities of previous maintenance and renovations leading to rot and vermin, ants in particular, but also a good season of mice. So this is our asbestos. The previous owners had confirmed that vermiculite insulation was in the roofs and had removed it. However, upon entering the house, we discovered these gray panels are also asbestos panels. And upon removing them, we discovered that there was vermiculite underneath those panels. So in the process, not only did we, that was the surprise because we knew this house was coming forward. So that little image on the left is us testing to see if asbestos was in any other areas of the house, either in the walls plaster or in the flooring. And everything was clear until we went up to remove those panels and then found vermiculite, which, horror story, is what can cause the cancer that is the fear of people inhaling asbestos, and it also upped the requirements for precautions during asbestos remediation. I'm happy to say that it was remediated as much as we could tell, and so far we're in the middle of the construction right now. We haven't found any more asbestos, so I think that horror story has been addressed. Radon. So we moved into this house thinking that this was fine. We we, by accident, our lovely contractor, Myron from Roos Custom Builders, asked if we might be interested in hanging this radon gas detector in the space. They had it kicking around. Let's try it. So we put it up and we got this reading 263.9, I think. But we weren't sure if that 9 was a decimal or not. And we knew that Health Canada sets 200 becquerels per cubic meter, per cubic meter as the maximum level for radon in the house. Um, Myron replied and confirmed that there's no decibel on this thing. We actually had a reading of 2,639 becquerels per meter squared in our house. So we were concerned. But this is an old radon meter, so we got confirmation from a secondary source. Before I go on though, so there it is, 200 becquerels, and at 600 becquerels per meter squared, you really need to take action. So we double checked. Radon, in case anybody doesn't understand, is a naturally occurring gas. It's radioactive and can cause and lead to lung cancer. And Manitoba, as you can see on the left, is a hotspot, no pun intended, of radon in Canada. So okay, let's be sure this is an old radon detector. Let's see what our secondary test will be, and it came back at 5,000 becquerels per meter squared. The margin of error was greater than the minimum level of radon that's supposed to exist in your home for a healthy environment. So right away, we could not get radon remediation instantly, but we were able to install a heat recovery ventilator, which was part of our plan anyway in trying to upgrade this house. So radon can be partially mitigated by installing a heat recovery ventilator, which at least exhausts and diffuses some of the air that's in your house and reduces your exposure. That is the photo on our left. And then the photo on the right shows the radon mitigation system that we were in the end able to do. And there were two sources potentially in this house. One was the sump pit, which you see pictured here. And then the other potential source was a dirt floor under our crawl space that we thought might be collecting radon from the ground. And here is the happy side of that. What you see here is our AirThings air quality monitor. And you can see in the red lines where we were before, up and well above 2,000, depending on the day. But where it drops is the day that we installed that heat recovery ventilator. Right away, it dropped the levels 1,000 becquerels per meter squared. And the day that we installed our remediation system just for the sump pit is that precipitous drop you see. Within 2 days, we were at an average of 25 becquerels per meter squared or cubed. So lesson learned here is of all the things you're looking for in a home, one of the things that we should be talking about is just getting an AirThings or some kind of air quality monitor or radon monitor and checking. We are in a hot spot and radon is invisible and it's natural, but it's also something we don't think about, and it has very serious long-term consequences. I feel I breathe easier in this home now. Okay, so to some of the other points that have been mentioned before, this house is beautiful, and we really appreciate its qualities being sheltered by mature trees and such. And so we were motivated to fix it. I think it was Jim who mentioned that you need a beautiful place to motivate people to fix it. Well, people previously had fixed this house, as you see here. They fixed rot by jamming it full of glue on the left. And on the right, you see an image as we're starting to do our exterior installation for our deep energy retrofit. They fixed the rot by replacing it with plywood, but didn't fix the original problem, which was the windows and the flow of moisture off that sill into the building wall. So those sketchy repairs, of course, ended up causing rot. And you can see this was on every single window. And the right picture is even the structural elements were rotting out because of poor installations and maintenance practices. So this is our chance to really do a job for this house and repair it. In the process, however, when you allow rot to enter into your home, you also introduce wet conditions. And these are just two of the windows. All of the windows indicated showed rot. And also really half measures, as you can see, the insulation on that left image too, which led to vermin. A lot of the walls that we found or excavated were full of ants because of the damp situations. And I don't know about you, but when we unearthed this, all of us were totally creeped out. Never mind that structurally, this house was being literally eaten from the inside. Horror story indeed. So was it worth it? There are other stories here, but those are probably the biggest pieces. We came into this project knowing that this house needed work. Um, and after our EnerGuide review test, the current was, as you can see, um, pretty high and much higher in terms of energy consumption um, than the new typical house. There was a potential that was prescribed to bring us down to 82, I think that's gigajoules per year. We're aiming to beat that and taking the house off natural gas and bringing the energy consumption from 174, which it was only a year ago, to less than 60. And that would be in the range of what this house was consuming in electrical power with gas. The house consumes just electrical power, had consumed 52 gigajoules a year, and we're going to get close to it with our renovations, we think, through modeling, but not quite that low. So what lessons did we learn? This house is and still is throwing curveballs at us, but we stay focused on the reasons why we're doing this renovation. Because as Jim says, it's the total cost of ownership, and it's also the longevity of the home. And for us, it was also preservation of the site and its natural forested, mature forest. So we're staying focused on the reasons why we wanted to do this renovation. And also to understand that when you go looking for trouble, which is kind of what we knew we were getting into when we bought this house, you hope for the best and plan for the worst. And so we're still going through with a good contractor in Roost. We're still going through and keeping our calm because we planned for the worst and have planned for a big contingency. And then also, I guess this kind of connects with Don and Ed as well. Don't repeat the mistakes of the past. Learn from them. And what we saw here was half measures now only makes the house want to kill you harder later. So that's what we've learned, and there's much more to learn from this house. But I think we're gonna get there.
All right. Well, thank you so much. I understand that it is now 1 o'clock, and so I do get that some people have to leave, but I do want to give people the chance to answer some questions or sorry, ask some questions. So if I'm just adding all of our speakers back, and is there anybody who has a question? You can just raise your hand or give a shot to unmute yourself. Also, just adding to the chat a survey that we have here that as some of you know, SBM is trying to do some guides on how to do some home retrofits. So if you've gone through something, share your experiences with us so that we can make sure that the guides are as consistent as possible, as based in reality as possible, and so that we can help other people not repeat these mistakes of the past. Okay, Mike, do you have a question? Do you want to unmute yourself and ask it?
Thanks very much. Yes. I w- what is the value of an energy advisor if you've had a chance to work with one?
You're asking me. Well, I think what was great is that the energy advisor, by doing this initial survey, gave us a really good um, picture of what this house was doing, how it was actually performing, and how it performs relative to the other houses. The assessment also gave us a checklist of things that we could do to reduce that energy consumption to the target. I think that that image shows that we could reduce reduce the energy consumption to 82 with the measures that we took on. Now, we wanted to do better than that. I had set a more stringent goal, but it certainly is all the things that they recommended. We just did them plus some.
Thanks very much, Cindy. But I did mean that as a general question.
Yeah. So anybody else have anything they want to add to this question um about energy assessors? I think that Cindy covered a good answer. Oh, Donna, are you we would okay, just readjusting. Sorry. All right. Do we have any other questions that anybody wants to ask? I think the presenters did a great job of bringing us through, so no problems. All right. Well, it doesn't seem like we have any more questions that I can see, or people who are adding them to the chat. So I guess that's it, folks. Well, thank you so much for your time here today. Thank you so much to all of our presenters. What an incredible amount of information that you shared and some lessons learned. Really, like, how do we stop repeating the same mistakes? How do we learn the lessons? So keep tuning into SBM for more on all of this stuff as we try and figure out how to bring more sustainable building to Manitoba. So, three cheers to everybody. Thank you to all the presenters and to everybody who shared their stories and read them out. And we'll see you next time. We've got a really exciting Lunch and Learn coming up. We don't want to share it yet because we're still confirming our speaker, but everybody we've told about so far went, ooh, that's an interesting one. So keep reading our newsletter, keep your eyes on the socials, and keep talking about sustainable building with all your friends and colleagues. It's one of the biggest ways that will make the difference. So have a great day, everybody.